Okay, so in this video, I'm going to talk about convergence in Taylor series. So we're going to find the first three non-zero terms of the Maclaurin series for the functions f equals sine of x times natural log of 1 plus x, and then we're going to determine where the series converges absolutely. Okay, so I kind of want to unpack like I think this is a question that like messes with people, and I don't think that it like needs to. So let's start with this first part, first three non-zero terms. Okay, so to do this, the easiest way to do this is to know this series and this series. So I am going to omit how to find this because I'm assuming if you watch this, you're kind of familiar with building a Taylor series. And if you want to see some examples of that, I have other videos on that. I'm just trying to keep this video short. So for sine of x, this series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, so on and so forth. So I can write this series like this. So I have -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. Okay, so I have this series, and then the other series that I have is this natural log of 1 plus n, and so natural log of 1 plus x. So this is x minus x squared over 2 plus x cubed over 3, so on and so forth. So this one I can write as -1 to the n minus 1 over n times x to the n. So I know that the indexes are a little bit off. Don't let that scare you. You can always adjust the indexes if you wanted. So I could change this to 0. So then this would be n, this would be n plus 1, and this would also be n plus 1. So maybe I'll just go ahead and state that. So these two things are equivalent. So I partially just stated this in two different ways because I think it's normal to see these in two different ways. And so I just want to make sure you kind of know, like these are literally the same, right? So don't panic if the index is different. Okay, so I am just going to make us uncomfortable and have these two different indexes so that we just roll with it and we don't panic about it, so we're used to seeing this. Okay, so the first part of this question is about these first three non-zero terms. So that is literally asking us then to take this series times this series and multiply them together. Now, there are several ways that you can do this. You can take the time to actually find the derivatives and find the first three non-zero terms. I don't feel like doing that. So I have other videos where I show you how to do that. I instead want to show you how to multiply these two series. Okay, so let's just like visually write this out for a moment because I was talking to somebody and I kind of understand why this could mess with a person. Yes. Okay, so let's see. Okay, so I've written out a couple of terms just to help me visualize this. This is now literally this series times this series. Okay, so what this is really asking for is for you to go through and multiply this, and what is that going to look like? So if I wanted to multiply out a few terms, so I just need to now put like my algebra hat on for a moment, and I just kind of need to think about like the nature of these terms. So in general, to multiply two polynomials, this is an algebra thing now, right? I'm going to take this term times each term in here. So I'm just going to do this for the first three terms. Okay, so I have x times x, so that's x squared. I have x times x squared, so that's x cubed over 2. And then I have x times x cubed, so it's x to the 4th over 3, so on and so forth. Okay, so I'm not going to continue this on for forever. I have kind of enough to establish the pattern. And now what I want to do is I want to pivot to the next term. So notice what happens when I multiply out the next term. So I'm going to take now this times all of these. Okay, so this is going to give me minus x to the 4th over 3 factorial. And 3 factorial is just 6, so I'm going to write that out for right now. And then this will become plus x to the 5th over, so 3 factorial times 2 will be 12. And then minus x to the 6th over 6 times 3 is 18. Okay, so this is actually kind of enough to help us establish the pattern of what we're trying to do. So you might have to multiply out a few terms just to kind of understand this. So what we're looking for now is we're really trying to go from like the lowest to the highest terms. So you have to think about now the nature of multiplying this stuff together. So I have x times x. This x squared is for sure the lowest exponent that we're going to get, right? So this is absolutely the first term. Now, the next thing to notice here is that x times x squared over 2, this is the only time we're going to get x cubed over 2, right? This is the only time we're going to get x cubed because this is starting with x cubed. So if I start multiplying anything else here, it's going to be higher than x cubed. So these are for sure the first two terms. And then the third term is where this gets a little tricky. And this is really why they're only asking for like a low number of terms so that you can kind of wrap your head around this. Okay, so I noticed when I multiplied x times x cubed over 3, so that gave me this, right? X to the 4th over 3. So the thing that you've got to wrap your head around is, will you encounter another x to the 4th power? And that's why multiplying out just a couple of terms can be helpful, because I then went through and I multiplied this, right, against everything in here. So taking this times this x produced another x to the 4th over 6. But now, after I get that x to the 4th, everything else is definitely going to be higher than the 4th, right? And that's the last time I'm going to hit x to the 4th. Because if I move on to the next term, I'm going to take this times all of this stuff in here. So you're looking for like those first 3 lowest exponents that you can get to. So I don't need these, right? Because it's not what's being asked. I just need these terms here. And now that I've kind of thought through how this series works, I know that these are going to be the only occurrences of x to the 4th. So now I can just combine these. So I can rewrite this fraction here. I'll rewrite this as 2 to the 6th. So now I've got 2x to the 4th over 6 minus x to the 4th over 6, so we can see how that's going to work out. So let me make some space. So I've just got those terms there. I'll just write a dot, dot, dot. Okay, so the first 3 terms are x squared minus x cubed over 2 plus x to the 4th over 6, dot, dot, dot. Okay, that is what we were asked to do. First 3 non-zero terms. All right, so tomato, tomato, I think at this point. Would it have been easier to just calculate the first 3 terms by finding derivatives? I don't know. I think this would be kind of difficult, actually. I know these 2 series, and I know it's a lot to kind of think through the first time, but I think this is one of those things like I can more easily do a little multiplication of polynomials than maybe having to take these derivatives over and over. But, you know, you do you. You were asked to find the first 3 terms. We found the first 3 terms. We're good to go. So now, let's pivot to the other part of this question. So determine where this series converges absolutely. So this can also be done from the original series themselves. So let me clear some space. And now, let's remember what we're actually doing here. At the end of the day, these are 2 power series, right? So I had a whole video where I talked about finding intervals of convergence with power series. So if I'm multiplying 2 series together, the interval of convergence will be the intersection of these 2 series interval of convergence. So maybe what we should do is focus on finding the interval of convergence for each of these. So let's do that. I'll make some space. Okay, so I have this series here. So let's just talk about like what would the interval of convergence be. So if you don't know, it is a power series, so just do the work to figure it out. So what I need to do then is I need to take the nth plus 1th term divided by the nth term. So let's see, if I do that, I'll have -1 to to the n plus 1, x to the 2n plus 1 plus 1 over 2n plus 1 factorial. Okay, that times 2 to the n plus 1 factorial over negative 1 to the n, x to the 2n plus 1. All right, so I also want to just go ahead and rewrite out what this is. So this becomes 2n plus 2 plus 1, and this becomes 2n plus 2. So let me just rewrite these. So this will be 2n plus 3, and this will be 2n plus 2. Okay, so now I can see a little bit more that I can do to this. So this, I can rewrite this 2n plus 2. I want to rewrite this. I'm just trying to make this so that I can save a little space here. So let's call this 2n plus 2 times 2n plus 1 factorial. So now I can see how things cancel out. So these cancel out. This will cancel out, so I can subtract 2n minus 1. And then this will cancel out with this. So what am I left with? Let's see. This becomes negative 1 x squared over 2n plus 2. Okay, so, and actually this time I don't even need absolute value here because this is being squared. So the last thing I need to do is take the limit as n goes to infinity. So this will equal 0. So that means that this series converges for on all values of x. So I'm going to write that here. So sine x, we'll just write we'll just write a note for ourselves. Okay, so now let's pivot to the natural log of 1 plus x. And maybe you want to do this on your own if you're practicing this. You know, I know it's tempting sometimes just to watch a YouTube video, but if you're trying to learn this, you'll get more out of it if you try it. Worst that happens is you get it wrong. So maybe pause here and then try it when you're ready. Okay, so to find the convergence for this series, so we'll do the same thing. So I will compute this and then take the limit as n goes to infinity. So this is going to give me negative 1 to the n, x to the n plus 1 over n plus 1, and then times n over negative 1 to the n minus 1, x to the n. So now I can see this is going to cancel out. Let's see, this minus n minus 1. Okay, so in the end, it looks like I'm left with n over n plus 1 times the absolute value of negative 1 times x. Yeah, just times x. So this negative 1 will drop out, so I can just write this as the absolute value of x. Since we're taking the absolute value of everything, I should have put that there. I always kind of end up doing it at the end. Okay, so now I can go ahead and take the limit as n approaches infinity. And so I talked about in another video that we really just treat the x as a constant here. So I can apply L'Hopital's rule. So this will be, if I use L'Hopital's rule, I'll just put the absolute value of x out in front. All right, so L'Hopital's rule is going to give me 1 over 1. So this just becomes the absolute value of x. And then we know to find the convergence of power series, we want to now set that less than 1. So here's my potential interval of convergence. And now I need to test each of the endpoints. So, okay, if I do negative 1, so this becomes negative 1 to the n for my x. Okay, so check this out. So now I've got negative 1 to the n minus 1, and then in this x position, I put in the negative 1. So now I can actually combine these two exponents. So I have n plus n is going to give me 2n. So let me rewrite this. So this becomes 2n minus 1 over n. Okay, so what does this mean? So this means then that my exponent, this is guaranteed to always be odd. So if it's always odd, this is always negative. So this really just comes down to being negative 1 over n then. So this is the negative harmonic series, and so this diverges. So negative 1 is not included. Okay, so let's get rid of that, and let's test what happens when x equals 1. So when x equals 1, if I plug x equals 1 into this, then 1 to the n isn't doing anything. So I'm really just left with negative 1 to the n minus 1 over n. So this is the alternating harmonic series, which does converge. So that is included. Okay, so what were we doing? So the interval of convergence goes from 1 to 1 here. So what were we doing? We were trying to determine where this series converge absolutely. So, okay, like I said, if you know the interval of convergence for each of these, then it's just the intersection. So what's the intersection then between all numbers and this interval? Well, it will just be the smaller of the intervals. So this interval of convergence then will be 1, or sorry, this should have been a negative. So this should be negative. Okay, so this goes from negative 1 to 1. So that's going to be the interval of convergence. So you literally just go back to what you know about power series to determine that, you know, and yeah, so that's it. Okay, so that brings us to the end of that example. If that was helpful, consider giving this a like, and I will talk to you guys in another video.